I think
We already live streaming in YouTube also, sir.
YouTube bol raha
YouTube.
okay.
Some participants are there in YouTube also.
Okay, okay.
Sir, shall I start the webinar?
Hmm.
Yes, sir. You can start, sir. Please.
A very good morning to one and all. Myself, N. Leela Prasad, Head of Mechanical Engineering Department at Vignan Institute of Technology and Science. I welcome all the registered participants to this today's webinar. And for today's webinar, we have a high-profile professor, Dr. G. Chandramohan Reddy sir, formerly principal MGIT Hyderabad. Now he is the professor of mechanical engineering at CBIT Hyderabad. Wholeheartedly, I thank and I welcome Professor G. Chandramohan Reddy sir to this one-day webinar. To this webinar today on a topic called Industry 4.0 Digital Manufacturing. Thank you very much, sir. Now I request my colleague Sai Krupa Madam to introduce our guest for today's webinar, Professor G. Chandramohan Reddy, sir. Thank you, sir.
Thank you.
Very good morning to all. I feel extremely honored to introduce the speaker of this webinar, Dr. G. Chandramohan Reddy sir. He is presently working as a professor in Mechanical Engineering Department, CBIT, served as a principal of MJIT on deputation during 2009 to 18, and contributed immensely for the expansion of UG and PG programs and obtained MBA, NAC, UGC recognitions to MGIT. He has 30 years of experience in teaching, training, research, and administration. He has published over 125 research papers in national and international journals and conferences of reputed and has successfully completed many research projects. And he has guided 7 PhD scholars and 2 scholars recently submitted, and currently he is guiding 10 scholars. He is a key resource person for and organizing secretary for 52 conferences and seminars and STTPs, workshops, FDPs, and conventions, and delivered 63 keynote guest lectures. And he was the chief and principal investigator for 4 research and consultancy projects. Dr. Chandramohan Reddy sir is the recipient of Young Engineer of the Year Award 1999 and Best Principal Investigator from AICTE New Delhi 2002, and Distinguished Alumnus Award from Kids Warangal 2007, and Best Technical Paper Presentation Award in 2008 by IEI APSC Hyderabad. Engineer of the Year Award 2009, Jewel of India by ISC New Delhi in 2011. An Eminent Educationist Award from International Institute of Education and Management in 2011 in New Delhi. Railway Board's first prize for the best paper at 27th Indian Engineering Congress held at Vignan Bhavan in 2012. ISTE Best Chapter Award in 2012 by Best Engineering College and Best Engineering College Principal Award in 2012. ISTE Best Student Chapter Award in 2004, and felicitated International on the occasion of Teachers' Day at III Khairabad in September 2015. And Best Paper for the category Best Presentation and Best Content at the ASAR International Conference 2016, and he is felicitated by the Department of Mechanical Engineering IIT Warangal on 7th October 2016 at their Golden Jubilee celebrations of PG program on machine tools. And he is also felicitated by Khairabad in September 2017 on Teachers' Day. Dr. G. Chandramohan Reddy sir relentlessly worked for the standardizing laboratory experiments in metal cutting, welding, and metal forming laboratories. And he is key member of core team of NBA accreditation in 1998, 2004, 2007, and autonomous work in 2019. Under his guidance, CBIT and MGIT obtained accreditation and life institutional membership of IEA. Visited Singapore in 2008 and presented 2 papers in international conferences. Chandramohan Reddy sir made remarkable services to the professional society, fellow of IEI, member of ASME, IEEE, AESI, ISTE, ISME, and TSI. He served as a joint honorable secretary and secretary of the Institute of Engineers, India, Hyderabad, and presently serving as a member of III Telangana State Center Committee, and served as a member of ERC in OU as and BOS in JNTUH Academic Council State Board of Technical Education and State Productivity Council SAC, and in 2000, from 2015 to 18, and TSMZ from 2007 to 18, and EC member of AESI Hyderabad from 2018 to 20. And Dr. Chandramohan Reddy sir currently working on optimization of process parameters for additive manufacturing of defense components, a research consultancy project of DRDO. Thank you, sir. Now I request Dr. Chandramohan Reddy sir to take over the session. Thank you.
Thank you, Mr. Sai Krupa, for the kind introduction. And good morning, all of you. Good morning, HOD, Dr. Leela Prasad Garu. And my own old friend, Dr. K. Chandrasekhar, and others who are present. And good morning, all the faculty. And I extend a hearty and warm welcome to all the participants for this very, very important lecture on Industry 4.0 digital manufacturing. So, I'll be briefly touching upon the trends that have taken towards the making it Industry 4.0, and mainly with the advent of digital manufacturing, the Industry 4.0 as a revolution, how it has started, all that you will see in my presentation. My presentation will last roughly about 70 to 80 minutes, and then later on followed by about 10-15 minutes question and answer session. So once again, welcome all of you. Then, see, I think every time I'm getting a disturbance, people are joining, and then I have to press the admit key. I mean, that role may be played by somebody else.
Yes, sir.
Okay.
We'll take care of that, sir. We'll take care of that, sir.
Right. Yeah, what is Industry 4.0 manufacturing? So Industry 4.0 manufacturing combines the automation. The automation has occurred as part of the Industry 3.0. And then you have the data technologies, and then integration of software equipment, and then people. People also play an important role with the making use of the smart technology. So the people and the use of the smart technology are a very, very important ingredient of the Industry 4.0. Another one is the data. The data transparency is an important component in Industry 4.0. The technology, this is one technology which has made transparency, the industry drawings, which were very much confidential, and then earlier through a protocol, they used to flow from top to bottom. So the different versions of the drawings, the latest version is made available to all through the digital manufacturing technologies. And then why it matters. So whenever you want to get something out, your question should be better. The better the question, the better the answer, the better the world works. So there has to be question and answer. Why Industry 4.0? Why Industry 4.0 matters? So that's the question that you need to put. And then the agenda for today's discussion is industrial evolution, fourth industrial revolution, building blocks of Industry 4.0, potential industrial products implications, potential consumer products implications, then impact of Industry 4.0. These are all the issues that we are going to discuss in our presentation. So I think all of you have seen this wet grinder, right? When you are, in the village, when you started your life, if not, the present generation, at least our generation, when we were going to school, we have seen this, that is a grinder. And then this is a water turbine. Most of you are aware, especially those who have got 1 acre, half-acre lands, they in order to get the water, this kind of technology was used. And then this is the one, floor mill, particularly when you require something to be made for during the festivals, right? Whatever the sweets and whatever the papads and whatever the things that are to be made for which you require the floor. So for that, floor mills, these are the floor mills. That is a certain level of automation. And then you have an automated machine. The earlier one is just it has got a electricity motor, and then you have certain automation level, segregation. Then there is what you call as separation based on the quality. All those technologies were used in this certain high level of automation. And then when you look at any design, the design may well be impossible to manufacture. So therefore, sometimes it may not be possible to manufacture at all. So therefore, the digital manufacturing has really enabled as to how a particular thing can be manufactured. So let us see what this video explains about this. What are the forces behind this transition from the conventional design to the
In this lesson, we will be focusing on why the transition from traditional manufacturing to a more integrated digital approach is happening. After this lesson, you'll be able to identify and explain at least 3 business and technical advantages
This
of the
is only
DMD
a
approach.
4-minute video. Please watch.
A major force driving the transition to digital manufacturing is economics. It's no secret that the US leadership in manufacturing has been eroding over the past few decades. What may not be known is that in 2001, the US trade balance for advanced technology products went into a deficit. This has multiple impacts, including jobs, the overall economy, and future competitiveness in advanced products. When the US loses our manufacturing base in advanced technology products, we then lose the ability to innovate on the next generation of those products, setting up a downward spiral. From a
Digital
business
manufacturing and
perspective,
design business benefits.
digital manufacturing and design benefits beyond impacting the balance of trade. For first-to-market advantage seekers, digital manufacturing and design allows for product design and manufacturing design to occur simultaneously, reducing the time required to go from concept to product. Another benefit of digital manufacturing and design is shorter product life cycles that address accelerated technology obsolescence. An example of this is how fast product lines are now turning over, like having new phone models every year. On the web 15 years ago, it took 3 to 5 years before a website was obsolete. Today, that's been reduced to 14 to 18 months. Obsolescence could be an entire topic to itself. For those interested in learning more, we have included some additional resources for more in-depth exploration of the topic as part of this course. A third benefit is addressing the social and political factors driving job creation and retention, often referred to as reshoring. As has occurred in other emerging economies, labor costs have increased in China by 13.7% between 2000 and 2015, making manufacturing outsourcing less attractive. As a result, there is now an opportunity to bring manufacturing back to the US. In addition to business reasons, digital manufacturing and design promises to overcome some key challenges facing the traditional approach to manufacturing. These challenges are: the physical separation of designers and makers has slowed innovation. Digital manufacturing promises to overcome this by creating real-time digital links between designers and makers. A second challenge is that barriers to sharing data and information have existed, both in terms of IT infrastructure and in terms of incentives skills, and IP policies. Labor costs are continually increasing, not just here in the US, but globally as well. And products are increasingly integrated and complex. These challenges can be overcome by using digital manufacturing to create a digital link between designers and makers, make connections between physical assets, machines, factories, and supply chains, reduce costs due to data aggregation and analysis, doing more with existing resources. These challenges and opportunities represent the driving forces behind the transition to digital manufacturing and design. The next lesson will begin to explore the overarching context for putting digital manufacturing and design into practice.
Okay, that is about what are the forces behind the transition in making from conventional design to the digital manufacturing. What are the issues when you have seen that? You have seen there. And then next, what is digitization? Say, digital information from multiple sources, formats, etc., to address key challenges of society in various aspects, such as health, education, weather, transport, commerce, government, and manufacturing. So it is a particular format, the information, putting it in a particular format from multiple sources uh, in order to address the various challenges in different sectors. So all those are indicated here. So here you have the industry, trade, defense, agriculture, rural sector. So all these areas. So you require to put it in a particular format to address these challenging issues. And then you have, see, we are talking about the digital manufacturing. You know what is digitization, digital information. Automation and digital entry into the manufacturing was also well discussed topic for the past 10, 20 years. Now at this juncture, you should know what is this little m manufacturing, what is big M manufacturing. Little m manufacturing is only manufacturing, is the conversion of raw material into useful products. The traditional definition, what you observe on the shop floor, is where work orders and the machine instructions are converted into hardware, where some removing the extra material in the form of chips. Whatever the components are made, that is called production. That is a little m manufacturing. But this big M manufacturing, you see, manufacturing is a process of converting ideas and market or customer needs into artifacts. Includes design, procurement, test, finance, human resource, marketing, fabrication, assembly, etc. The artisan of history performed manufacturing. Here you can see that little m manufacturing is only simply production. See, there is a drawing that is already existing for which you prepare. But this became is a very comprehensive term, comprehensively, right from the creation to the final product and product to use and then its disposal. Everything is included in this big M manufacturing. So therefore, it is the whole manufacturing when you say this is it. And then you have historical development of integrated manufacturing. You can see the first it all started with the mechanization, water power, steam power, that is the era that is called manual manufacturing. And then next era is the mechanization, the mass production, assembly line, electricity. This is the era of basically the 1920s, flexible assembly lines of 1920s where these fixed automation systems were existing. Then fixed automation, next stage is the programmable automation and the flexible automation. So that is the third level where with the use of NC and CNC, right from 1972 up to 2005, 2010, that is the automation. That is the industry 3.0, you can say, or third level of automation. And the fourth one is the present one. This is a combination of internet, nothing but the cyber physical systems and this integrated manufacturing systems resulted in this industry 4.0. And then, yeah, here also, So this will explain you some introductory concept of
Welcome to the first course in the Digital Manufacturing and Design specialization, Introduction to Digital Manufacturing and Design. My name is Ken English, and I'll serve as your guide as we explore this new approach to making products. After completing this lesson, you'll be able to explain what is meant by digital manufacturing, and also explain how digital manufacturing and design represents the fourth generation of the Industrial Revolution. To set the stage, let's take a step back to the first Industrial Revolution, ending in the early 1800s. This transition is often thought of as the
yeah, this is
Industrial
what
Revolution,
exactly I have
but
explained.
is actually the first of an ongoing sequence. The first Industrial Revolution was represented by the transition from manual production to mechanical production, enabled by the harnessing of water and steam power. The second Industrial Revolution came at the beginning of the 20th century, with the development of approaches that enable mass production, including the assembly line. The third Industrial Revolution, also known as the Digital Revolution, represented the advances made possible by automation as mechanical and analog technologies gave way to digital electronics between the 1950s and the 1970s. We are now entering what is being described as a fourth revolution, also known as Industry 4.0. Industry 4.0
IoT
is the
connected
next
factories,
phase in the
everything will
evolution of
come in this
manufacturing,
Industry 4.0.
combining the cyber capabilities resulting from advances in computing with physical systems to create a highly intelligent, interactive, and automated manufacturing ecosystem that integrates product design, manufacturing, and logistics. Now, a formal definition of manufacturing is the process of converting raw materials, components, or parts into finished goods that meet a customer's expectations. Manufacturing is the most tangible part of the product lifecycle because it results in a clear outcome. There are multiple definitions of the product lifecycle, most differing only in their terminology or details. For this course, we'll use the definition provided by Michael Greaves in his 2006 book, Product Lifecycle Management: Driving the Next Generation of Lean Thinking. Greaves defines the life cycle as all aspects of a product's life, from its design through manufacture, deployment, and maintenance, culminating in the product's removal from service and final disposal. The first stage in a product's life cycle is planning. This is where designers work through understanding requirements, whether they come from customer expectations, industry standards, or regulations. These requirements are then transformed into specifications, or technical requirements that can be measured. These specifications give you a way to evaluate initial feasibility of a product and whether the process should continue to design. Design is the product lifecycle stage where form and function come together to meet specifications. As you develop prototypes, whether physical or in a computer, design is where parts are created to fill the needs of the product. This begins in an abstract fashion with conceptual design and concludes with detailed design, where final, detailed part specifications are created. The next step of the process is to take the product from a design and build it. This stage includes when you define the items that need to be manufactured and how they'll be created and assembled. Production prototypes are created and checked to see if they meet performance and cost requirements, as well as long-term production capabilities are established. This is also where customers have a chance to evaluate the acceptability of a manufactured product. Once produced and purchased by the customer, the product must still be supported. The support stage of the life cycle is where you provide the customer with information to assist in the effective use of the product and maintain the operational performance of the product. A product's life cycle ends with disposal and recycling. The dispose stage of the life cycle draws on information from the design and build phases to understand the composition and what portions of a product can be recycled into future applications. As with other stages, the dispose stage may iterate with design as you work to develop a product that meets performance expectations and that can be disassembled at the end of life. Over time, multiple opportunities for improvement have been identified for traditional design and manufacturing processes. In a product's life cycle, many iterations may be required before customer approval is received. In traditional paper-based processes, information sharing can consume valuable time and delay the
Yeah, this
development
is one
process.
aspect you should
In
concentrate.
traditional
Information sharing
processes,
is a
there is
big
also a
one,
lag
big issue.
during and in between stages in the life cycle as necessary approvals are sought. Sometimes this can even result in losing first-to-market competitive advantage. Another challenge in paper-based processes is that maintaining a single source of truth for product and process definitions is very difficult and can result in limited capabilities for data analysis and evidence-based decision-making. Communication problems can result when plan changes are made during design and development process, as well as after the production launch. A new approach is digital manufacturing. This approach uses increased computing power to improve the product lifecycle. The Digital Manufacturing and Design Innovation Institute, or DMDII, defines digital manufacturing as an integrated suite of tools that work with product definition data to support tool design, manufacturing process design, visualization, modeling and simulation, data analytics, and other analyses necessary to optimize the manufacturing process. Deployed throughout the product lifecycle, digital manufacturing enables you to more quickly and authoritatively share information in the design process, with all the data generated in every part of the lifecycle representing a digital thread. This digital thread can be used to create a computer-based digital twin, an integrated system of data, models, and analyses that can be used in design, manufacturing, support, and disposal. These concepts all come together as the fourth industrial revolution, Industry 4.0. An example of the vision and promise of Industry 4.0 can be found in the wind power industry. Wind power is an important component of the clean energy industry. An ongoing challenge for wind farm operators is the significant wear and tear of gearboxes. Gearboxes are expensive to fix, especially after failure. However, if sensors on the turbine are linked with weather information and computational models, a very accurate simulation can be developed for each individual turbine, enabling evidence-based decision-making and the creation of predictive models for performance of individual turbines and the wind farm as a whole. This concludes the first lesson of digital manufacturing and design. As we continue this course, you will build on your knowledge of digital manufacturing and Industry 4.0, including career opportunities and forces driving the transition to digital manufacturing and design.
So you heard what is the reason for this industrial revolution and Industry 4.0 in specific. What are the advantages that it is offering? Several aspects you have seen. This is the reason why very good examples are covered in this video. That's the reason why I am taking the help of the videos. And then you have, next slide is, yeah, the industrial revolution. Yeah, end of the 18th century, we have seen what is called as the first industrial revolution, introducing mechanical production machines powered by water and steam, which you have called. Now we are seeing, after looking at different technologies, and then at this stage, I thought that I should clearly give you the conceptual understanding of what is Industry 1.0 to Industry 4.0, how the revolutions occurred over a period of time. End of 18th century, we had the Industrial Revolution, introducing mechanical production machines powered by water and steam, that is Industry 1.0. And then we had the Industrial Revolution, introducing mass production lines powered by electric energy, which we have called as Industry 2.0, beginning of the 20th century. And then you have the third Industrial Revolution, beginning of the 1970s, through the use of electronics and then IT, further progression in autonomous production systems. Then Industrial Revolution 4 or Industry 4.0, based on cyber physical systems, everything comes here. As of today, we are in Industry 4.0. Please understand that India could not catch any of these Industry 1.0, Industry 2.0, and Industry 3.0. But as a country, we should be proud. Everybody in the audience should be proud that in Industry 4.0, when it started occurring, we are on par. Our contribution cannot be neglected. Our contribution has to be as a country, the technocrats, the engineers, the IT professionals, they contributed immensely for the implementation of Industry 4.0 across the globe. So one round of applause for all our people that we are really on par when it comes to Industry 4.0 as on date. And then you have phrases of earlier three industrial revolutions. You have basically 1760 to 1840, it all ushered in mechanical production, railways, and the steam engine. And 1870 to 1940, the mass production, electricity, and assembly lines. And 1960 to 2010, computers, semiconductors, mainframe computing, personal devices, internet kind of thing. But when the integration with the cyber physical systems occurred, then we have got what is called as the Industry 4.0, and you have got the number of case studies here. Industry 4.0, as followed as practiced in Germany, a smart manufacturing leadership position with USA, a collective term for technologies and concepts of value chain global organization. Based on the technological concepts of cyber physical systems, the Internet of Things and the Internet of Services, it facilitates the vision of the smart factory. Within the modular structured smart factories of Industry 4.0, cyber physical systems monitor physical processes, create a virtual copy of the physical world, and make decentralized equations. Over the Internet of Things, cyber physical systems communicate and cooperate with each other and humans in real time via the Internet of Services. Both internal and cross-organization services are offered and utilized by participants of the value chain. So this Industry 4.0 builds on the digital revolution, and it makes use of the smaller and powerful sensors, and it makes use of the concepts of the machine learning and ubiquitous internet, and of course artificial intelligence is the backbone for this Industry 4.0. And there are labor and energy costs are saved by using this Industry 4.0. And then you have, when you look at these particular technologies, they did not exist in 2006. For example, iPhone was not there, iPad was not there, Kindle was not there, 4G was not there, Uber, Airbnb, Android, then Oculus, Instagram, Snapchat, WhatsApp, all these were not there in the year 2006. Now, time to reach 100 million customers, if you take telephone, has taken 75 years to touch 100 million customers. International, of course, our World Wide Web, www. Whatever you type on the websites. So it has taken about 7 years to reach 100 million customers. Facebook took about 4 years to touch 100 million customers. Instagram took about 2 years. Pokemon Go, it only has taken 1 month time to touch 100 million customers. And then cyber physical systems, which we have been talking about, it involves the computers, it involves the communication and then control. So this is the cyber physical system. So the key is the central point is the information. A cyber physical system is a system of collaborative computational elements controlling physical entities. CPS are physical and engineered systems whose operations are monitored, coordinated, controlled, and integrated by a computing and communication core. They allow us to add capabilities to physical systems by merging computing and communication with the physical processes. And then today's factory, if you see, any manufacturing facility, if you see, sorry, yeah. So it is rigidly sequenced car manufacture and production. It is more or like a fixed automation. The processes will go in a very fixed sequence. That is today's factory. And then tomorrow's factory, if you see, decoupled, fully flexible, and highly integrated manufacturing systems. See, for the operations to happen and then complete, they need not go in a particular sequence. They follow the principle of line balancing. to complete the cycle, and they need not go in a particular cycle. Okay, fine. Yeah, these top controls are obstructing my slide. It's okay. We will go ahead. And then Industry 4.0, there are 6 design principles. Interoperability, the ability of cyber physical systems, that is workpiece carriers, assembly stations, and products. Then humans and then smart factories to connect and communicate with each other via the Internet of Things and the Internet of Services. Virtualization, a virtual copy of the smart factory, which is created by linking sensor data with the virtual plant models and the simulation models. So virtualization is very much used in conceiving this Industry 4.0. Decentralization, the ability of cyber physical systems within smart factories to make decisions on their own. Next is the real-time capability, the capability to collect and analyze data and provide the insights immediately. Next is the service orientation, offering of services of cyber physical systems, humans, and then smart factories via the Internet of Services. Modularity, see, everything is modular in Industry 4.0. Flexible adaptation of smart factories for changing requirements of individual modules. And then we have building blocks of Industry 4.0. If you see, there are many, like okay, there are say building blocks. You require autonomous drivers, and then simulation, horizontal and vertical system integration, industrial Internet of Things. This is IIoT. IoT, IIoT is Industrial Internet of Things. Cyber security, additive manufacturing, and then augmented reality, big data analytics, all that, they are all building blocks for the successful implementation of the Industry 4.0. So let me take the help of some videos. Yeah, you can see this particular.
How do analytics fit into the industrial Internet of Things? I'm Dave Froning from SAS, and I've loved manufacturing for more than 20 years. Industrial companies wrestle with really difficult problems, from complex supply chains to motion applications to labor constraints and equipment breakdowns every single day. For manufacturers, solving problems is nothing new. However, with IoT, competitive organizations are finding new cost savings and revenue opportunities. Instead of their flood of data becoming an overwhelming challenge, with analytics, it's become an asset. Analytics help operations sense what's important, understand where value can be generated, and act immediately to capture that value. Specifically, manufacturers are using analytics to predict impending equipment failures, improve quality and market responsiveness by coordinating extended and complex supply chains, and better engage with their customers to develop new revenue streams through enhanced product features and new product development. Streaming data presents one of the biggest opportunities. SAS is helping industrial companies extract value, whether their information is sitting neatly in a historian or flying by in a high-speed operation. For example, by looking at information from SCADA systems, MES systems, and LIMS systems, even weather data, manufacturers can gain fresh insight into what conditions lead to production rejects. More importantly, they're now able to deploy that understanding in the form of a model that runs against the streaming data as it's being produced. This provides the earliest indications of a potentially costly reject condition and allows them to mitigate the causal factors in time and improve profitability. If you want higher yields, better quality with lower costs, and the opportunity to create new revenue sources with your IoT data, contact us. we're proud to help manufacturers extract the value from the industrial Internet of Things.
I hope you understood something about the industry Internet of Things through this video. Now, there is one more we are seeing that connected factories, and then let me check whether I can play some more videos to explain certain other concepts. Yeah, of course, this how it works, the Internet of Things and then manufacturing. This is a different aspect. I think
The Internet of Things has the potential to increase global productivity up to 25% by 2025, which could translate to an economic value of $11 trillion. Industries like manufacturing are embracing the potential of the Internet of Things. Many production facilities are already using processes and supervisory control systems with connectivity. The Internet of Things for manufacturing is a family of solutions that combines the capabilities of analytics, cognitive computing, and the Watson Internet of Things platform to drive operational efficiency across the factory value chain. This solution benefits the manufacturing industry in three main ways. First, it helps plants get 100% efficiency out of their equipment by identifying and solving issues before they cause delays. Second, it makes processes and operations cognitive, so plants can produce maximum quality and yield from raw materials and manufactured components. Lastly, it helps plant managers better manage resources, improve worker expertise, and provide a safe working environment. Advances in these three areas define a new wave of connected manufacturing, one that revolves around things, process, and people. Let's take a look at how this works for Simon, the plant manager for an aircraft manufacturer. Simon oversees the production of key components for large commercial aircraft, and his top priorities are meeting production deadlines and producing airplane parts safely and efficiently. One of his biggest clients needs to move up their delivery date by 3 months. Simon and his team use the Internet of Things for manufacturing, which will help them deliver earlier than originally planned. An equipment analytics solution identifies problems with equipment health and performance before they happen and prescribes maintenance procedures so Simon's team can avoid equipment failure and downtime, getting maximum effectiveness out of their equipment. To ensure the components are meeting quality standards along the production line, Simon uses a quality analytics tool to identify variability in the manufacturing process in real time. This allows equipment operators to make adjustments to process parameters based on plant conditions that could affect the quality of production. By monitoring quality in real time, Simon's team can avoid producing faulty components, ultimately saving time and money. Another priority Simon has to account for under a rush schedule is the safety of his plant workers. The cognitive IoT platform includes worker safety technology that monitors things like exposure to extreme heat or toxic gas, open flames, and operating dangerous machinery. The plant workers wear sensors in their helmets and wristbands that provide real-time alerts on working conditions, activating preventative measures if physical well-being is compromised or safety procedures have not been applied. Because the platform allows Simon to track all of this Internet of Things data in real time, he can be confident that the production equipment, tools, and employees will be able to safely take on an accelerated schedule and make plans to move forward. Once the completed aircraft from Simon's plant is put to use, those manufactured parts continue to generate data over time, data that designers and engineers can use to make improvements and updates to each part in the future. Additional sensors also make it possible for Simon's plant to offer cognitive solutions to the airline to help with ongoing predictive maintenance of each manufactured part. Using the power of the Internet of Things paired with cognitive computing and analytics, companies across all industries will improve the way they design and manufacture connected products. Products that will change the way we work and live.
okay, that was about how Internet of Things contributes to the proper sensing and identification, and then really improving the safety and other aspects of the workers in the factory. Now, so this there are a number of building blocks, and then how to overcome some of the videos I've explained you, and then going forward, see how this impacting all aspects of value chain, right from the engineering design tools to the life cycle, customer relationship, then global communication, enterprise resource planning, supply chain management, factory infrastructure. So everything is being impacted by this industry 4.0, the sensors, actuators, every aspect of it is, this is a value chain in the digital manufacturing. These are all impacted with the use of digital manufacturing. So, and then we have, and then, so once again, value chain related video I wish to play. How everything is getting impacted.
This lesson focuses on the effects of digital manufacturing and design on the ability to manufacture products, especially when multiple distributed organizations are involved. Let's consider something simple, like this pen. This pen is a BIC Pilot G2. BIC is the organization that manufactures the end product, what we purchase. A term for BIC's place in the enterprise that creates this pen is the OEM, the original equipment manufacturer. The OEM relies on suppliers to manufacture and deliver components that can be assembled. These suppliers purchase component parts from other suppliers. This can repeat many times, getting to the most basic components of a product, like the ink in this pen. These suppliers are referred to as Tier 1 suppliers or Tier 2 suppliers, etc., referring to their place in the structure that provides components that are assembled into the pen. The supply chain refers to the system of organizations involved in creating a product. Products of any size have a supply chain. Consider the Boeing 777, a very large and complex airplane. As the OEM, Boeing manufactures the final product. In order to manufacture this end product, Boeing purchases large shock absorbing assemblies from a Tier 1 supplier, ITT Enidine. ITT Enidine purchases machine pistons from a small machine shop and gets them chrome plated at a small plating shop to enhance surface properties. The machine shop and the plating shop are examples of Tier 2 suppliers. Next, we have two videos that highlight concerns that can result from a complex supply chain. Please watch the videos and take a moment to consider their impact. For the 777 to be manufactured with the right quality, in the right amount of time, and at the right cost, it is critical that all organizations in the supply chain communicate effectively. This communication includes timely information sharing with the right stakeholders. Rather than relying on paper documents, a digitally enabled supply chain allows design documents, part revisions, and purchase orders to be shared electronically. Redesigned components can be checked for fit without having to produce a single part, saving significant time. A way to think about this impact of the DMD paradigm is the right data in the right place at the right time, enabling quick and correct decision making. This focus on the timeliness of data reduces the impacts of a change that can lag in time and grow in scale as it propagates through the system. Sometimes this is known as the bullwhip effect. An example of this is how, in 1994, a strike at a single brake plant ended up shutting down major portions of GM's vehicle production. DMD reduces the effects on the supply chain by transparently sharing efficiency information, whether man, machine, materials, or methods, throughout the supply chain. Increasing supply chain confidence between tiers. Reducing excess inventory that's contained within the supply chain. And allowing for realizing more efficient and agile supply chain models. This lesson described the impact that DMD has on the supply chain. These benefits are among the forces driving the transition to a digital manufacturing and design paradigm.
Yeah, in digital enterprises, the entire value chain is digitized and integrated. You can see here in the digital world, to the real world, you can see without having to do really, we can complete everything in the digital world. There is a product design at this stage, and you have the production planning, production engineering, production services. All these things are completed in the digital world before they really go into the real world. So entire chain is digitized and then integrated. That is the advantage of digital manufacturing. And then potential implications are robot-assisted production, predictive maintenance, additive manufacturing of complex parts, machines as a service, big data drive quality control, production line simulation, smart supply network. These are all the potential implications of the digital manufacturing. And and then you have if you look at the robots working in Amazon warehouse, if you see how the number has significantly increased right from 2013 to 2016, and at the present, the number can be much more. This is everybody is moving towards the digitization, digital manufacturing. Of course, robots are an element in the automation. And the automation is a subset of the digital manufacturing. And then you have the Siemens is one example. German manufacturing giant Siemens, an industrial user, is implementing an Industry 4.0 solution in medical engineering. For years, artificial knee and hip joints were standardized products, with engineers needing several days to customize them for patients because every product is unique that has to be customized for. Now, new software and steering solutions enable Siemens to produce an implant within 3 to 4 hours. So this is made possible by the, of course, additive manufacturing for the purpose of manufacturing, and the rest of the activities associated with the manufacturing are supported by the digital manufacturing. Trump is another example. German toolmaker Trump, an Industry 4.0 supplier and worldwide market leader of laser systems, has put the first social machines to work. Each component is smart and knows what work has already been carried out on it. Because the production facility already knows its capacity utilization and communicates with other facilities, production options are automatically optimized. Predix is another example of GE, the operating system for the industrial internet, is powering digital industrial business that drive the global economy. By connecting industrial equipment, analyzing data, and delivering real-time insights, Predix-based apps are unleashing new levels of performance of both GE and non-GE assets. And then evolution of product and the process design, if you see how it was done in the 80s and then 90s, right, towards 2000, we have been using the simulations for the purpose of design and the validation of the manufacturing process. And of course, 2010 and onwards, we are using the digital manufacturing of the certain things that we have already discussed. And the next one is the examples of product evolution, connected and the smart product. The Philips lighting, users can control Philips lighting light bulbs via smartphone, turning them on and off, programming them to blink if they detect an intruder, or dimming them slowly at night. This particular technology is being used in Medtronics. Implanted digital blood glucose meter connects wirelessly to a monitoring and display device and can alert patients to trends in glucose levels requiring attention. Rolf Raleigh Polo Tech shirt, available in 2015, streams distance covered, calories burned. So the examples of product evolution connected. See, all these Bebenet, they play pure drive product system, put sensors and connectivity in the tennis racket handle, allowing users to track and then analyze ball speed, spin, and impact. So these design, see, innovation and development of certain advanced products made the implementation of the digital manufacturing, right? Then coming together is the beginning. Keeping together is progress. Working together is a success. This is told by none other than Henry Ford, the world's giant manufacturer. Now, at this change, at this point of time, I wish to ask all the participants, what is digital manufacturing? Digital information from multiple sources, formats, owners, etc., for the enhancement of manufacturing. So you are getting the information from multiple sources in the digital form and different formats from different owners for the enhancement of manufacturing. I'll put one question. Is digital manufacturing a new one? No, it is already there. In 1990s, in the form of application of digital information for the enhancement of manufacturing process. And in 2000s, the application of digital information for the enhancement of manufacturing process and supply chain. And in 2010 onwards, the application of digital information from multiple sources, formats, and owners for the enhancement of manufacturing process, supply chains, products, and then services in this form, it has been there. So digital manufacturing is not new. It has been existed in different forms in the past. It is only consolidated now. So this is how you see the engineering process for product realization, product requirements and specifics, you see design synthesis, design representation, design analysis, design evaluation, and then the manufacturing planning, and then manufacturing execution and execution. So this is the engineering process for product realization. Then in this product design, see the costs involved are 5% only you are spending on product design, and 50% on material, 15% on labor, and about 30% on overhead. But the influence you can see, product design influence is about 70%, and 50% of the material is only having finally 20% effect, and 15% labor can only have 5% effect, and 30% overhead can only have 5% final effect. But who casts the biggest shadow? It is the product design that has to be correct, that has to be improved time and again to suit the trends that are taking place all over the world. So that is made possible. The product design, the flexibilities, and all those things are taken care by the digital manufacturing. And then big three in a production cycle are the design, production, and the process planning. The evolution and the manufacturing of any big product is outcome of these three activities. And activities in a production cycle, you have the design operations, planning operations, and then production operations. Design consists of preliminary design, drafting, design analysis, synthesis, analysis and optimization, evaluation, presentation, resource requirement, project engineering, build prototype, design directives and layout, design information. And at the planning stage, process planning, process plans, how to make, where to make, tool design, tool fabrication, and then proving it, NC programs, picture book planning. So pictorially you have to give the planning, estimating, planning information. And at the production operations stage, it is production planning, production controls, factory controls, NC tools, fabricating, assembly, test and inspection, material handling, and producibility information. So these are all the activities in a production cycle. So here the CAD/CAM integration and the computer assistance to the production. So same thing, the previous one, if you put link it to the CAD/CAM and then in the pictorial chart, it appears like this, right? There is a product concept, and then you make use of the computer-aided design, computer design, engineering, drafting. This will follow customers and markets. These are quality, production, scheduling. These are all the follow. Finally, there is a computer process planning, and then so everything is integrated in this particular fashion, and we have the CAD/CAM integration, computer assistance provided to the production cycle. And then same thing, earlier design operations, if you see the earlier slide, there are conventionally happening, but the same thing with the computer assistance, computer-aided design, computer-aided drafting, computer-aided, all these design operations, CAPP, and then CAM. Now CAD/CAM activities that earlier design, planning, and operations has resulted with the assistance of the computer design, computer-aided design operations as CAD, planning operations as CAP, and production operations as CAN. So in this particular fashion. And then boundaries between functions in traditional manufacturing. These are the business, there is a production, there is a engineering, there is a human resources. That boundaries are very much there in the traditional manufacturing. But redundant data cause manufacturing problems. See, sometimes uh, data that is not accurate and data that is not equivalent, they all cause problems. That is always happening in the conventional manufacturing. This can be really overcome in the digital manufacturing. Information flow from design to production happens in this particular way. See, tool design, and then there is a tool design work has to be done, a supplementary activity to the product design manufacturing, and then the flow is like this. So how the information sharing is a very, very critical element here. The how it is done in digital manufacturing systems, you will see information sharing. Yeah.
As we continue working through a high-level view of the digital manufacturing and design paradigm, we get to the topic of how information gets shared between groups, whether machines, suppliers and manufacturers, or customers. After the lesson, you'll be able to explain the role of data and purchasing communication standards in manufacturing and design, including real-world scenarios where these standards can be applied. Why are standards relevant? Why do we need to be aware of the technical details of transferring information? Consider a simple example, a single manufacturing shop floor. The shop floor has several computer systems and manufacturing equipment of varying ages, each generating different output. The individual pieces of equipment are creating data in different formats for various reasons, like systems from different manufacturers have output in proprietary formats as part of an effort to lock in future software and hardware purchases. However, if we need to establish a relationship between two different data sets to create information or connect machines from different manufacturers, they cannot be in different formats. That's what data standards do. They specify a consistent data format so the data can be shared and transformed into usable information. Some examples are STEP and
It is a
IGES
format.
are
IGS is
data
a format.
standards
STEP is
for
a
sharing
format.
product design data like geometry. MT Connect is a standard that supports the capture and sharing of information from machining equipment. MIL standard 31000A and ASME
These are all the standards.
1441 define a way to share product model information using a technical data package to support the product lifecycle. To complete learning about standards and their place in the digital manufacturing and design paradigm, we're sharing two additional items in the resources section. The first is a video on MT Connect, and the second is a very informative website for the MIL standard 31000A.
Yeah, common database for a manufacturing system. So this is related applications utilize the same data. So that is possible to maintain in a, because we require that same data can be used by engineering section, human resource section, the business people, the production people. So this is possible through this digital manufacturing systems. Common database, how it is maintained, human resources, production, business, they can draw from the any change that is accommodated, that is always reflected and that it can be shared by everyone connected here. And then you have the cyber physical system at this stage, after advancing to such a level of understanding of digital manufacturing. CPS is a system of collaborating computational elements controlling physical entities. CPS are physical and engineered systems whose operations are monitored, coordinated, controlled and integrated by a computing and communication core. They allow us to add capabilities to physical systems by merging computing and communication with physical processes. So this is about the cyber physical systems. And then you have the life cycle considerations in product design. If you see, there are life cycle design. If you see recycling, need, product design, manufacturing assembly. This is in the lower circle, and these are enveloped by the bigger circle: working conditions, resource optimization, life cycle cost, company policy, product properties, and then ease of manufacturing, environmental protection. These are all issues. And then you have manufacturing trend. If you look at the mass, everybody is moving towards the mass customization. The meaning of mass customization is that when you go to a shop, you and yourself, your colleague, if you go to car company, you will buy the same brand and same car, but each one asks for different features. Some ask for manual windows and some ask for powered windows. So each customer satisfaction is nothing but the making them suitable for each customer is mass customization at no extra cost. Suppose if the basic thing is costing about 6 lakhs, the separate facilities that are provided for each customer that should not cost more than the 5%. Suppose 6 5s are 30,000. So if it is costing you 6 lakhs, it should not cost more than 6 lakhs 30,000. So at only minimal and minimal extra cost, you should get additional features that is unique to yourself. And then this is 1850 to 1913, you have the mass production, and 1955 also mass production. Then you have the customized mass production. Customized mass production is making in large number to a particular segment of customers. But when you are targeting each customer, that is called mass customization. Then mass production versus mass customization. The era of mass production was there up to 1980s, and then now we are moving towards, now we are in the era of mass customization. Mass customization has the ability to produce a single and customized product with the same efficiency as a mass-produced component. IT and flexible work manufacturing processes allow customization of goods or services. Contrary, mass customization also increases unnecessary cost and complexity. So there is no need to produce, great number of the customized products. Collaborative customizers conduct a dialogue with the individual customers to help them articulate their needs, to identify the precise offering that fulfills those needs, and to make customized products for them. Adaptive customizers offer one standard but customizable product that is designed so that users can alter it themselves. Cosmetic customizers present a standard product differently to different customers. Transparent customizers provide individual customers with unique goods or services without letting them know explicitly that those products and services have been customized for them. Impact. So the impact of this on economy, business, national and global level, and the society and the individual. So that is already evident impact of this changes in digital manufacturing, including mass customization. And how it impacted the economy, the growth, aging, productivity, employment, labor substitution, the nature of work. So it is impacting the economy in a bigger way. Impacting the business. There are customer expectations. There is a data enhanced product, collaborative innovation, and the new operating models. So this is how it has impacted the business is shown in this. And then workforce. Workforce, let us see how it impacted the workforce with the help of the video. Okay, I think the impact on careers. This is, yes.
In this lesson, we will be focusing on how the transition from traditional manufacturing to a more integrated digital approach will impact the workforce. After this lesson, you will be able to better understand how DMD will impact the workforce and career opportunities. In manufacturing, the workforce has evolved over time, following along with the industrial revolutions. First, as artisans who handcrafted entire products one at a time. Then, as a skilled workforce, specializing in individual components of a product, like the suspension system of a car. Eventually, workers are seen as a blended workforce, where the focus continued to be on the manufacturing skills an employee might have, with some post-hiring training in continual quality improvement, like understanding the principles behind Six Sigma, or learning to operate multiple machining centers to increase efficiency. Operators are still seen with an open-loop perspective. The focus is on my machine, just processing materials to generate output, without any opportunity for feedback to impact the end product. Digital manufacturing and design envisions a workforce highly engaged with the creation of the product. From invention through to disposal, workers will need to understand how their actions impact design, manufacturing, and logistics. Workers will also need to use analysis tools and advanced machining to efficiently produce products, especially in a mass customization environment with a high mix of products, each with a smaller batch size. These changes shift the focus for digital manufacturing and design from only tooling and machining skills to workers that also have skills in technology, operations excellence, and people skills, or the ability to effectively collaborate with others as part of a team. Some items to keep in mind when considering the impact of the digital manufacturing and design paradigm are: the National Institute of Standards and Technology, or NIST, estimates that 600,000 manufacturing jobs are unfilled in the United States because of the lack of high-tech manufacturing skills among job seekers. According to the Society of Automotive Engineers, SAE, over 98% of all products will be developed digitally by 2020, which makes this skills deficit even larger. Small and medium-sized enterprises, SMEs, consisting of 1 to 500 employees, represent 95% of our nation's manufacturers. But 94% of SMEs have not adopted high-performance
Small and
digital
medium scale
manufacturing practices.
entrepreneurs.
All this means that the opportunity to create a new generation of a workforce that is excited about and competent in digital manufacturing and design methods is very real. This shift may result in changes in job titles. Manpower is working with the DMDII to identify and update job titles impacted by Industry 4.0. Titles and responsibilities for drafters, CNC programmers, machinists, especially those using manually controlled equipment, document control specialists, inspectors, and testers performing visual and manual inspections will all change. Not all current job titles will be impacted. Tool and die makers, as well as inspectors for highly critical items that just cannot be inspected by digital means, will have minimal impact. Additionally, new job functions will be created. Others will emerge as the Industry 4.0 revolution continues. But we do know there will be a need for employees with skills in advanced manufacturing, agile, robust, integrated manufacturing, modeling and simulation, including model-based systems engineering, or using the digital thread to minimize multiple designs or prototypes or test iteration, intelligent machines, using self-aware manufacturing hardware, smart sensors and controls to develop instrumentation for legacy equipment, and use big data analytics. Advanced analysis. These are jobs in high-performance computing, designed for manufacturing, integrated smart design tools that reduce over-engineering. And finally, cyber physical system security. These are trusted networks, gate and IT controls, or ISO 27001. The DMD revolution is going to open up even more opportunities for a skilled workforce, creating a market for higher paid workers who use their knowledge to impact the creation of the next generation of advanced products.
Okay, now you know the importance of the creating the workforce for the uh, next generation digital manufacturing. I think all of you accept the fact that the rather than the machining and then tool skills, it is the technological and people skills and collaborative skills that is the order of the day. And then if you look at the impact, national and global, governments, countries, regions, cities, and international security, all these are affected. And then society, there is inequality, community, the individual, which identity, morality, ethics, human connection, these are all the areas, which are impacted by these technological revolutions that are taking place. Our 10 skills to be relevant in Industry 4.0 are like this. In 2015, these are the complex problem solving, coordinating with others, people management, then critical thinking, the negotiation, quality control, service orientation, judgment and decision making, active listening, creativity. These are all skills required in 2015. But in 2020, complex problem solving, critical thinking, creativity, people management, coordinating with others, emotional intelligence. So that is not there earlier. This is added here. Judgment and decision making, service orientation, negotiation, cognitive flexibility. So these are all the issues that are required in 2020. And then, of course, something about the data security and the disaster recovery. This is the one aspect that I need to focus right now. This is
As we wrap up this module on data storage in the digital thread, it would be wrong of me to go through all of this content without speaking to some of our worst fears. With that in mind, I'd like to ask you to stop and reflect for a moment. What's the worst thing that can possibly happen to the information that makes your daily progress possible? This isn't just in the context of the digital thread. Think of the things that could truly bring you or your organization down to its knees. Something probably instantly came to mind. Dig deeper. That's probably not the worst thing that can happen. With 1 foot in the world of information technology and 1 foot in the world of mechanical engineering, I have a fairly unique perspective on the lessons to be learned that make the adoption of the digital thread possible. In the information technology world, there's a large focus on security and disaster recovery. There are people whose entire job it is to think of that question I just asked of you, to really think about the worst case scenarios. When I think about worst case scenarios, it generally revolves around the destruction of a location. Whether that be from fire, flood, or some other disaster, it means that the place from which I operate becomes completely unusable. Some examples of disasters are natural disasters like earthquakes, tornadoes, hurricanes, etc. Major fires, whether man-made or from a natural influence. Large-scale power outages, massive hacking attacks, or major computer failures. And it can even be some update goes badly and brings down all of your production equipment. In the most extreme sense, you could think of the terrorist attacks like on September 11th, 2001. In addition to the massive and tragic loss of life on that day, multiple companies learned painful lessons on the realities of IT disaster recovery. From one news report, more than half of all small to medium-sized enterprises affected by 9/11 did not trade again. Merrill Lynch, who we might think of as a large organization with a well-funded IT department, lost 2 data centers on September 11th. Merrill has now decentralized its core IT systems, making them more robust to failures. Although the term disaster makes us all pause, the good news is that this is a well-explored area, and guidelines have been developed that make implementing approaches straightforward. A good disaster management strategy is basically an insurance policy against low likelihood, high consequence events. How do you develop a disaster management strategy? There are some key aspects. A disaster management core team should be established. This would be a group of stakeholders with responsibility and the necessary authority to develop and implement the disaster management plan. Risk analysis needs to be performed to look at risks that could cause major disruptions, possible causes, and worst case situations, and how likely they are to happen. This is also the point where timelines to the restoration of normal operations can be set. This practice should sound familiar to those in design and manufacturing who have experience in hazard assessments. Once risks are identified and likelihoods defined, then priorities need to be established to develop.
Yeah, again, let me quickly come back to my PPT. I mean, the data security disaster recovery are very, very important that has to be incorporated. So the possible calamities and all that is explained in this. And the vision of digital manufacturing and the design, how it should be, in the changing world, what kind of vision and a company should have in terms of the digital manufacturing. So you may let us see this. I think mostly this is the final video, digital manufacturing vision. This is only 3-minute video.
Take a moment and think about a friend or colleague who does not have a cell phone. In addition to feeling disconnected from the rest of the world may think of them as disconnected. People can even come to ask, how do we stay in touch? Now combine that thought with the idea of seamlessly sharing information throughout the life cycle of a complex product. Large integrating manufacturers, or OEMs, will expect that all of their suppliers use technology to increase efficiency and effectiveness. In fact, these requirements are already being incorporated into the bidding processes for contracts. Those who are not digital need not apply. This module focuses on the ideal digital manufacturing and design world, with an ever-present digital thread at its center.
Digital thread is
Some
another
years
concept.
ago, there was a Defense Department program review where one of the attendees stood up and mentioned that now that there was a requirement to use a digital technical data package, or TDP, the number of bidders dropped by 50%. That means that just based on the conditions of the contract, even if they produced a world-class product at a great price, some companies just could not compete. And that was quite a few years ago. In many areas of industry, the digital thread is well on its way to adoption. As with other advances like supply chain management and Six Sigma, once the benefits are known, others will adopt the innovations as well. Many of the components of the digital thread will be incorporated like trade secrets. Competitors will just get faster and produce better products. At the same time, companies are increasing the expectations of their employees beyond manual labor. When I say manual labor, this doesn't just include physically lifting equipment and products, it also means controlling equipment like machining centers. A reality that exists is that manual labor costs are lower outside the US, making going offshore an option to companies that look at keeping unit production costs low. Instead of lowering labor costs, an alternate approach is to increase productivity, producing more products with the same workforce, often with some form of automation. This relies on the willingness of the workforce to innovate, adapt, and take more responsibilities within the production process, both in design and in manufacturing. In the next lesson, we'll introduce the diffusion of innovation and give you the opportunity to assess where.
Okay, I think you witnessed the several aspects of digital manufacturing with the help of the most advanced videos made by State University of New York at Buffalo. Now, our lecture has come to the conclusion. So these are my details. I mean, you can come back to me on any of these notes, either by email or by mobile. any doubts that you may have later on. Also, if you want to talk on these, if somebody is willing to work in these areas, they can always, they're always welcome. And now it is over to organizers. Maybe we can pick up some questions from the audience.
Yes, sir.
Very fast, yeah.
So now questions will be read by Dr. Singarwal, sir.
Yeah, please.
Please, sir. We have received some questions, sir.
Good afternoon, sir. This is
Good
Dr.
afternoon.
B, Associate Professor of Vignan Institute of Technology and Science. Thank you for your very informative presentation, sir, with the live video example.
Yeah.
We have few questions, sir.
Yeah, please.
Sir, suppose in BTech level, MTech level, student project in digital manufacturing area.
Yeah.
We want to give means how to, and also in sir.
Yeah, it is like this. Those who intending to do BTech project, the primary requisite is that they should understand what is digital manufacturing, very clearly about the digital manufacturing, and that in that what exactly they want to do. They want to contribute something in the area of IoT or in the area of product design. With the help of computers. I mean, there are people even outside also. I think academic level we can decide the course of work to be done, and then there are based on some specific need that is required. Maybe the autonomous control of a robot in the work environment or whatever it is. So for that, the specific assistance from the manufacturing can be taken. Yeah.
Sir, suppose IoT, Internet of Things, additive manufacturing technology, robotics. Students, they are doing project.
Part and of the digital manufacturing. Yeah.
If you suppose doing project in the specific area,
Yeah.
this is called digital manufacturing areas. It is also called.
So it is like this. If somebody is working on additive manufacturing, it becomes additive manufacturing. It will not become digital manufacturing. Digital manufacturing is if one is working, doing something, that kind of information is made available to everybody in the product life cycle. The product, see, right from the conceiving, the design to the product design to the manufacturing and then to the final stage and its disposal at the final disposal and at every stage. So the information is transparent and it will be shared to everybody in the product life cycle. So that is the speciality of digital manufacturing. Most of the time, what happens is at student level, they mistake additive manufacturing as a digital manufacturing. Certainly not. Digital manufacturing may use additive manufacturing as a manufacturing, but without additive manufacturing also, digital manufacturing will exist. Okay.
Only final question, sir. It is almost similar to first two questions. Some faculty advertisement, they have mentioned faculty with digital manufacturing specialization.
Digital manufacturing specialization, maybe I don't know whether any of the IITs are offering in digital manufacturing. Of course, I am just doubtful because digital manufacturing, which has emerged as a revolution, those who are practicing only can do something at this moment of time. Not really, no universities, but only in the US it is there. Digital man. Maybe you can do. I mean, those who are interested, they can do in Coursera. This course is there. Digital manufacturing. Digital manufacturing. I have done one course in digital manufacturing and design, and I have also done one more course on digital thread. Digital thread. That is the next level. These two courses I have done on Coursera. Those who are interested, they can do in Coursera. They can register and then complete. Actually, before going for any project, let them complete one or two courses on Coursera from the USA universities. Okay, right? Yeah, please.
Thank you, sir. Thank you once again. Now I will hand over to Professor Dr. K. Chandrasekhar, Vignan Institute of Science, for a vote of thanks.
Yeah.
Thank you, Dr. Singarwal, sir. Now, Good afternoon to one and all. So it's my privilege to propose vote of thanks and acknowledge the contribution of those who worked hard to make this webinar a grand success. On behalf of management, principal, and Department of Mechanical Engineering, first of all, my sincere thanks to today's eminent resource person, Dr. G. Chandramohan Reddy Garu, Professor of Mechanical Engineering, CVAT, and former principal of MJAT. Sir has accepted our invitation in spite of his busy schedule. And thank you very much, sir. And I
Thank
thank
you,
all the
sir.
participants for patient listening during the webinar. I also thank our HOD of Mechanical Engineering, Professor Leela Prasad, and all the faculty of Mechanical Engineering. So special thanks to Dr. B. Singarvel, K. Vijay Kumar, P. Sadanandam, Anup Kumar Jana, P. Vinod for their excellent support for this webinar. So once again, thank you all. So thank you, Dr. Chandramohan Reddy sir. Thank you, sir.
Thank you, Andy. Thank you very much. Thank you. Thank
Thank
you,
you,
the entire
Dr.
team.
Chandramohan Reddy, sir.
Thank you, Andy. Thank you. Thank you, all of
Thanks,
you.
sir. See you.
Thank you, all of you.
And one more information to participants, we will post at what is a feedback link, so in the WhatsApp group, so that you'll get all certificates. So today it's possible to get only 100 certificates. Remaining certificates we'll give you tomorrow. So thank you very much to all participants, and a special thanks to Dr. Chandramohan Reddy sir. Thank you, sir.
Thank you, sir. Thank you, all of you.
Thank you,
Thank
sir.
you, sir.